Here's another problem. We have a 24-tooth gear, and this gear is spinning around at 6,000 RPMs. It then engages a 36-tooth gear, which is going to reverse direction, but it's also going to have some angular velocity. The question is, what is that angular velocity of the 36-tooth gear? Well, we don't really have a relationship for this, but we can probably figure one out. We do know that the teeth of the first gear times theta for the first gear will be equal to the teeth for the second gear times theta for the second gear. However, if we were to take both sides of this equation and divide by delta time, I'm going to use capital T for time here just to keep things clear. The time that both of these gears turn will be the same time. So it's not like a delta T1 and a delta T2, it's just delta T. But the change in theta with respect to time for each of these things is angular velocity. That's really what it is. And so we could rewrite this. We could say teeth 1 times omega 1 is teeth 2 times omega 2. And then we could use radius instead of teeth, and we could use diameter instead of teeth if we wanted. So this is another relationship that you might want to consider putting in your toolbox. The product of angular velocity and teeth or radius or diameter is constant. Well, let's apply that to this problem. First of all, there are 24 teeth in the first gear. Its angular speed is 6,000 RPMs. That would have to be equal to 36 teeth times whatever omega 2 is. So you solve by dividing both sides by 36 teeth, and you'll find out that omega 2 comes out with units of RPMs as 4,000 RPMs. There's another relationship that's often quite useful, and we can develop it by taking a look here at the definition of omega, its change in angle with respect to time, and the definition when we're using radians of what theta is. It's delta D over R. So if we substitute delta D over R for theta in this relationship, we find out that we've got delta D over R over delta T. But that just simplifies really to delta D over delta T times R. Well, we know that delta D over delta T is velocity. So therefore, we can rewrite this thing and we can say that omega is equal to V over R. And that's another relationship that you might want to consider putting in the toolbox. Omega is V over R, ties together the linear speed and the rotational speed. So the linear speed of a point on anywhere on the rotation compared with that radius has a relationship to omega. So here's an example problem that makes use of this. A car has wheels that are 15 inches in diameter and it's going 30 miles an hour. What's the angular velocity of the wheels in RPMs? Well, here's the setup for our problem. Omega is what we're trying to find. Omega is V over R. We have a little bit of a unit problem because this is in miles per hour and R is in inches, and so we've got a unit mismatch. I think we can fix that by taking velocity and turning it into inches per minute. That's what we want to do because we're supposed to come up with RPMs or revolutions per minute. So let's do that here. 30 miles per hour. We know that an hour is the same as 60 minutes, so that changes our time unit. And we know that a mile consists of 5,280 feet, and we know that there are 12 inches in a foot. So with all this put together, we should be able to find out what is our V, but in inches per minute. That comes out to 31,680 inches per minute. Probably shouldn't have that many significant figures, but I'm going to go with it. So omega then is 31,680 inches per minute divided by the radius of the wheel? Well, it was a 15-inch wheel, so its radius would be half of the diameter, 7.5 inches. Inches are going to drop out, and I'm going to get omega in per minutes. When I do the calculation, I find out that it's 4,200 radians per minute. But I want that revolutions per minute, so I'll do a little conversion here. 4,200 per minute. And I know that there are 2 pi unitless radians for every revolution. So dividing 4,200 by 2 pi will give me 668, and that's revolutions per minute, and that's the unit we're looking for.